Hi everyone, thank you for coming to the talk. I hope you're all well caffeinated and ready for more talking. The talk is Design Space Exploration with Focus on Predictors. As it says, my name is Karl. I am a first-year PhD student, and the goal with my research is not to create more predictors, but to change how we do research in predictors. So I'd like to start by taking a bit of a macro picture at the current state of predictor literature. So some of you may be familiar with some of these or all of these, but I think most people that have ever sort of looked at any work on predictors will know one thing. They're really complicated and they're really hard to understand. And this has sort of led us into a scenario where there's two camps in the sort of space of predictor literature. Either you have predictors where we sort of forcefully have had to come up with good ideas, something like branch prediction, where it's such an important component for IPC that we've been forced to come up with very efficient designs, even though it's very difficult. However, if you look at the current research, most of the ideas are based on sort of original ideas stemming from the mid-2000s. You have ideas like Tage or Perceptron, and really we've just sort of settled these last 20 years for sort of fine-tuning those designs or adding small auxiliary components. Alternatively, you have the other camp where you have things like value predictors and memory dependence predictors, where these have never really fully taken flight. What sort of happened is you have a very sort of sparse research and people have not really gone into this field. Again, I think just because there's this perception that prediction literature is really difficult, someone else will be doing it, and so people are more sort of content just fine-tuning existing designs rather than creating new ones. And this is what has sort of led me to ask this question of whether or not we're currently in a local minimum. I think there's a lot of reason to think that that is the case. And so the next question becomes, how do we move on from that? And that's what I'm going to try to talk a bit about today. And I'm going to start by focusing on a type of prediction that fell in the second camp of sort of, I think, slightly under-researched. So I've picked memory dependence prediction. That's what I've worked on for this like half year or so. Just a quick summary for those that are not familiar with what memory dependence prediction is. It's really just a predictor that is responsible for, in any CPU that has a store queue, to guess when you're issuing a load whether or not that load is dependent on a previous store. If that is the case, you have a data hazard and you need to stall your instruction for a little bit. Alternatively, if your predictor thinks that is not the case, you can speculatively issue your load, which leads to IPC gains. Of course, this last scenario here, if you speculatively issue a load, but it turns out that there is a dependence, you pay quite a high penalty in having to squash everything. So with the current literature of this, the first paper on memory dependence prediction came out in '98, and so I think I've identified roughly 4 or 5 unique designs after that. Just recently this year, in March, a new design came out that achieved state-of-the-art performance by quite a significant margin. When I came across this paper, I thought it was quite impressive. They had a lot of good ideas, but I also thought that there was room for improvements in the paper. And so this was the point where I thought I should go and create my own predictor, which I did. But I don't think today it would be interesting to talk about what that predictor actually looks like. I don't think that's super relevant to the talk. Instead, what I want to talk about is the approach I took for creating the predictor. So I started out with this thing I've deemed here approach 1. So what I did here is I think this is the traditional approach. You come across some paper or you have some idea where you say things are not working quite right at the moment. And so you build some kind of new design that you then test out. Then you run it on a bunch of traces, you simulate it, you see what comes out, you see where it performs well, where it performs poorly. You try maybe 3 or 4 designs and you settle in on something ultimately that you're happy with, and then you say, well, that's great, this is my new design. So this was the approach I started with, and happily I beat the state of the art, which was a big sort of happy moment. I was quite happy, yeah. But I wasn't really happy with the sort of ad hoc way that this went about. You sort of left questioning, did I really end up with a proper good design here, or did I just get sort of lucky? So after having done all of this, I wrote down a list of all the features I'd added and removed throughout the design stages. I wrote a set of parameters I'd sort of tried, and then created a set of like 1,000 candidate predictors. I then just ran a basic grid search, and it improved the speculative errors, the expensive errors, by a further 14%, so leading to an even better design, and sort of showing that my squishy human brain could not really compute against just a simple search space algorithm here that's not really complex in any way. All right, so what are the learnings from this? I think the point of this small story here, even a little bit of automation in design-based exploration goes a long way. By no means is grid search novel or anything like that. I'm sure it's been done many times before. But I think it's interesting to ask whether or not we could take it further, right? As I pointed out here, predictive research is really difficult, and especially this thing of just relying on experts in different fields of different silos of prediction means that perhaps we're missing out of lessons in, say, for example, we have really smart branch predictor people. That does not mean that we're really far ahead in, say, memory dependence prediction. And this is why we need help from machines, I think. So the question I want to ask is, can we rely on machines to explore even larger sections of the design space? And to answer this question, the first thing you want to consider is what kind of roadblocks do you run into? And the answer here is, I think there's two major ones you need to overcome. The first one is you need more general descriptions of predictors. So what I just described, sort of a parameterizable design with a few different parameters, it's too narrow to say that what you're really doing is sort of creating novel designs. This is more akin to just fine-tuning, so you want something wider than that. Alternatively, doing design-based exploration across entire hardware description languages is likely to not be fruitful or too difficult. ChatGPT is really good, but we're not really at the point now where it can write, say, a novel predictor in Verilog. It's just not there yet. Maybe it will be soon, but I think another thing to consider as well is that simulating many possible designs is expensive, and I think the right road to take here is using ML to more aggressively prune the search space. So next, let's try to think a bit about what the future could look like. So what I'm looking into at the moment is I've taken the sort of parameterizable design I had earlier and asked, what's this sort of on an abstract level? And I ended up creating this highly abstract, sort of very parameterizable design for a memory dependence predictor that has 2 to the 32 configurations. And some of you that have done this before might say, well, that's not inherently impressive. That's 4 8-bit integers. But in this case, the idea is not so much to you're not just trying a bunch of different integer values. The goal here was to try to cover as many designs as possible that are interesting. And in this space, you have encoded fully not just the predictors that I had made earlier, it also encodes the space of the previous design space predictor. So that's just a bunch of parameters away, essentially. And it also covers the predictor prior to that, the state-of-the-art. So you essentially have 3 generations of state-of-the-art memory-dependent predictors within the space, which means that I think it's more interesting to explore. To go even more extreme, I've pulled this paper up from the past. Some of you might look at it and say, well, 1997 is quite a while ago, and I would counter by saying yes, but I still think it is interesting and it was underappreciated at the time. So the paper is called A Language for Describing Predictors and Its Application to Automatic Synthesis, and it basically does exactly what the title says. So they create a language in which you can write predictors. I've given some examples on the left-hand side of the slide here from the paper, where they write sort of relevant predictors at the time, things like a simple 2-bit predictor all the way up to G-share, which was a state-of-the-art predictor at the time. What they did was they went a step further and they used sort of ML algorithms of the time, genetic algorithms, to automatically synthesize new predictors. They're actually surprisingly competitive for a 90s ML algorithm with sort of these human designs. They actually achieved second place in sort of a list of known predictors at the time. And I think it's interesting that in this design space they created, the best predictor of the time was still encodable. So this was more a limit of the design space algorithm rather than the design space itself. And to think just sort of where all this could lead us, I want to consider a bit that I think there's still so much room for getting more creative with how we design predictors. And I think the reason we haven't done it again is just because it's so difficult, and you either typically just end up with fine-tuning things or having to build things from scratch. If this was not the case, if we can be aided a bit more by sort of automatic design space exploration to make things easier, we can get into difficult things like, say, communicating between predictors or sharing information, just to sort of think of some of the opportunities there, right? If you think of a branch predictor, what that is essentially a model of where your computation is going to be going in the future, whereas the prefetcher, its whole job is to front-load computation that's going to be happening in the future. There seems that there would potentially be gains in sharing information between these, but you have these siloed areas of research, which is probably why it's not something we've seen a lot on to begin with. So just to quickly summarize what the win would be, well, if we get good at automating design space exploration on a small scale, what this potentially would yield is just that we would more cheaply be able to fine-tune predictors for different workloads. I think even this is a win on its own. Typically right now, even fine-tuning predictors is sort of something that's been the job of experts, but perhaps there's gains in just, say, having a branch predictor fine-tuned for different kinds of workloads. So you can have a different branch predictor for, say, a server, a mobile phone, or a data center. If we're able to explore larger sections of the design space, perhaps we're able to yield sort of novel designs with better performance or lower energy. And ultimately, if we can have machines sort of aid us in this design, we can create maybe novel designs that can, like, such as new hybrid or combined predictors. So I put a quick summary of the talk up here, and I would like to finish by saying my thanks to Rob and Tim for supervising me in my first year, and thank you for listening.